Hello, everyone. My name is Caden Plew, and I'm excited to have the opportunity to share with you today something that I've been working on with colleagues of mine in regards to transient system analysis of Gen3 particle-based CSP plants, and in particular, the effect that the hot particle storage bin has on the performance of those plants. So I'll jump into my slides here and give you the rundown of what we have here. Okay, so this work, the foundation of this work lies in a prototype system which is being developed at San Diego National Laboratories right now, of a CSP power plant that uses particles as the heat transfer fluid to transfer the solar energy input to a supercritical CO2 Brayton cycle. Okay, and in this work, we're particularly focused on the salient physics of the hot particle thermal storage bin and how those physics affect the rest of the system. So this is a brief diagram of a model that we have in Modelica that shows the system performance that we're looking at here. And we also have the ability to couple this with a MATLAB model that we've made to capture the salient physics of hot storage bin. And these are kind of the domains that we're looking at when we're modeling those systems. Okay, for charge and hold. For charge, we have an inlet flow rate of 9 kilograms per second, and it charges over a duration of 6 hours, and then it's held for 10 hours, and then it discharges at a rate of 5 kilograms per second over a period of 8 hours. Okay, so all of these modes have to be considered, and we need to understand how heat is being lost throughout each of those modes. Okay, for the charging and holding solutions, okay, we've essentially come up with a way to model this using Newman boundary conditions. The center line, of course, is just a zero flux, and then Robin at the top. Okay, so we have convective and radiative heat transfer to the surroundings and the air inside of the bin there. And solutions can be deduced to standard solutions that have been developed and published a long time ago. Okay, we also need to consider the composite wall and how that's being charged and allowing heat to pass through it. So at the end of the day, this is kind of what we can expect from our models. As far as the important heat transfer modes, and how those heat transfer modes go on to affect the outlet temperature of those hot particles that are eventually going to be drained and go into the heat exchanger. Okay, so the outlet temperature is, of course, the thing that we're most interested in, because these are the hot particles that are going into the rest of the system. So in charge and hold, the outlet temperature is just defined as like a bulk temperature at the orifice, but of course it's closed and no particles are flowing out. During discharge, we can see here that we have a peak, and that's coming from the temperature profile that you saw on the last slide, where we have heat loss on the exterior and then we have a hot core. Okay, and then it drops down. We have a minimum where the coldest particles are flowing out, and then the rebound, of course, is dependent on the ratio of heat loss at the top to the ratio to the heat loss at the walls. Okay, so like I said, this outlet temperature is extremely important to us because it affects the performance of the heat exchanger. Okay, and any modulations in that outlet temperature need to be compensated in order to maintain a steady operation of this heat exchanger and maintain a steady outlet temperature for the supercritical CO2 passing through there. Okay, so you can see here that the simple system that we've been modeling in Modelica does a relatively good job with this, maintains an effectiveness of about 0.75, but of course this comes at a cost. We need to input some energy for any marginal deficiencies that we have in that particle outlet temperature. And that comes just from a marginal heater that we have underneath the hot storage bin. So you can see here that with that input, it changes the efficiency, and we can see a maximum difference in efficiency of about 4%, which, as you probably know, an efficiency difference of 4% can be a major thing in power plants that are operating 24/7 all times of the year. So with that, I'm going to conclude and leave it up to any more discussion or questions that you may have. Thank you, and